your heart.
We're going to do the same thing. So we made a file just for NF-kappa B binding. You guys will notice when we use bed tools that we're going to need a GTF. We're going to do the same thing by making a GTF that's specific for chromosome 22. Again, this is just going to kind of make our jobs smaller, make it go a little bit faster. You can use the same principle, you can use grep. And it might be useful, since this is a HG19 annotation, to keep this annotation file in your HG19 annotations folder, as opposed to your NF-kappa B projects folder. But whatever makes sense to you is good. Oh, I guess the other thing I didn't tell you, this is another bash command that I use sometimes. WC is, it counts things in the file, so if you specify -L, it's going to count the number of lines in the file. If you don't specify -L, I believe it gives you an output of like number of characters as well, or something like that. So I can use WC-L followed by a file name to count the number of lines in a file, and here I'm going to see that I should have 702. So you guys can check your NF-kappa B file that you've made by counting the number of lines and checking it to make sure that NF-kappa B is the only protein that you have in there.
Get ourselves into the annotation of HG19 further from this command here.
Well, if you're grepping for a file and you're not in that folder, is it going to find it? But you could also provide a full path. And it would find it. Yep. Same type of thing. Same rules apply. Full paths or being in folders. Yeah? Okay. I don't know. Yeah, I always just do it regardless. But I just put it into a CC called source of destination. But I don't do a lot of information on here. So I'm not sure what all it is. Like, what your start from this one. But if you go to it's not that. So you use that second part. So your source file is there. This is your response file. And the destination to CC code is how's it going?
All of that is telling your Jupyter notebook that's in Python to change the language to bash. So this code here is now in bash and not in Python. So just try to read it as Python. That's all that is. If you're gonna if you're just gonna do it in that terminal, you can stay in bash. You don't need to tell it to be bash. Every time there's another class.
Okay, so
It did.
yeah, that's good, but you know, it doesn't work.
Okay, so you cannot use the paths that she's using here. Because first of all, we didn't call it TF finding bed. We just called it TF.bed. And so you have to put the path for where you put it.
Yeah.
She said, don't do the test.
I was trying to just edit my own that where
although I probably didn't need to do that because I specified it anyway, which is show me like the top rows of this spot here. But actually didn't need to specify properly right now because I already drew it. Is that where it is? Or did you put it in whatever? You probably don't have it in that. I would see go LS. What's in your projects file? Like 99% of the time I just scroll chat. So actually that's why I was using Jupyter to actually look at my file. File architecture, you know, because I can't remember it. I did do, yeah. You think like my history, like and then the other 10 are checking on my status. And I always do
There's a lot I can do. That too, that's more like given the virus and the virus but that's me why
Yeah, you can. Yeah. Yeah.
this model now it's
Okay, looks like you guys are doing okay, getting through some of this stuff. I want to introduce something that I'm not going to spend too much time on, but again, this is something that can be very useful and very powerful. It's also very easy to get bogged down in the annoying syntax of this, so it can be difficult to use. I like what it can do, so I try to use it sometimes, but even when I'm using it, I'm like, where does all this stuff go again? It's hard for me to remember and read. But knowing what it does is useful because there's so many examples out there on the web that you can copy syntax from to figure it out. So awk is a way to extract lines in a file other than grep. So we just used grep, and what grep does is it takes any row that contains whatever character you gave it, and it keeps that row in your final file name. So we were grepping for NF kappa B, and that was fine because NF kappa B only existed in one column. But if you had an instance where, say, NF kappa B existed in the column that specified protein name, but it also existed somewhere else in the file that was not related to the protein name, and you wanted to specify that you want to look for it in a certain column instead of anywhere in the file, that's when you use awk. So awk will go line by line, and you can specify, I want to look in this column, and if it has that value in the column, then I want to keep that row, or I want to print columns 1, 2, 4, 5, and 8 of that row. It's very interchangeable. You can do a lot of stuff with it. I've included some examples here that I've taken. This was a tutorial that somebody else in our lab wrote, explaining just in general how you would do it. So the syntax is always awk. This dash capital F specifies the delimiter of your file. So by default, it will be tab, but you can also specify. So if you have a comma separated file, you would change your delimiter to, I believe, -C. But again, all this information is on Google. The point is you have to specify the delimiter. And then here is the action that's going to be carried out. It's in quotes and it has these wiggly brackets. And so in this case, we're just printing everything. And then the final thing that you're going to give is the name of the file that you're operating on. So in this instance, we would print everything in this file. You access columns with awk using a $sign. So in this instance, we're only printing the 8th column in this file. We're saying, okay, we've got a tab delimited file. I want to extract the 8th column. This is the way that you do it. If, say, we want to find the length of our genes, so we always have this syntax where we have start and stop, and the length would be stop minus start. We can use awk to go through each line and do that subtraction for us and print the output. So for example, awk, if we want to say length is equal to the value in our 5th column minus the value in our 4th column, and then we're going to print length on that file. Who can tell me what this is doing at the end? Yeah. Mary?
Going to the top lines.
Okay, and what's this? What?
That's not break between the.
It's a break. Why is this
The
here?
heading of the.
Yeah, it's a pipe. Right, we're piping the output of this into this. Okay. There's more examples here. I don't want to get bogged down in the syntax of it other than just show you guys that it exists. And we're going to use it here. So we're going to use it to, using awk to parse GTF files can be very useful. And there's lots of Google information out there about how you would do this. I'm showing an example here that we're going to use in this annotation file. So what we're trying to do is we're trying to get promoters of transcripts. So first what we need is a list of transcripts. And you remember in our GTF file, we had exon ID, we had UTR, or we had exons, we had genes, we had UTRs. And the other reason that we're having to do this is because, okay, so you'll notice here this column is defining what the feature is. So we want all of the ones that are transcript. But if you scroll over, each of the exons has an associated transcript ID. So if we just use grep in this file, we're going to get all of the rows back. So we specifically want to do a grep on this column. So we're going to use awk. Yeah?
When counting column numbers, does it get a 0 or 1?
1. 1 for awk is 0 for Python. Just have to keep track of what you're doing. Okay, so the way that we're going to do that is we're going to use awk. We're going to specify that we have a tab delimited file. And we're asking the question, if the value in the 3rd column is transcript, then I want to print. And this 0 that's here means to print the whole line. So if I just wanted to print a specific column, I would do print followed by the column name. With awk, if you use 0, it's going to print the whole line. And we're going to do this operation on our annotations file. And we're going to save the output of it to a new annotation file called chromosome22.transcript. So once you run this, take a look at your transcript file. You can look at the number of lines in it. You can look at it with ~S, makes it easier to view. And you can see how this works. So we asked the question if the 3rd column had the value transcript. We wanted to keep the entire row in that GTF file, which will give us a GTF file that's specific to transcripts on chromosome 22 and not any of the other information that's in there.
Does it double equals just mean matches exactly, or
What?
does the double equal sign just mean match exactly?
The double equal sign is associated with when you're asking the question, like if this equals, then do it. If you're assigning something to a variable, say set this as, it's only one equal sign. Yeah.
What is the print $0?
So print $0 will let you print the entire line. It might also work if you just do print. Probably will. But yeah, yes, you mentioned that the columns start with column 1 counting. So 0 means the entire line. But if I only wanted to print, say, the first column, I could specify print column 1. if any of you guys have any problems making these files, but you still want to be able to go on to the next things, I can put them in the shared directory. Hopefully you guys were able to follow these to make these files and you know where they're located. And then I'm going to kind of set you guys free and encourage you to work with the people around you to do this new thing. And I'm going to try to do it with minimal instruction. We've only got an hour left, so we may or may not get through the whole thing, but I've provided you guys the instructions for what you're going to be doing in here and pointed you to the right spots of where you're going to need to be doing this from. So just kind of like as a brief overview of what we're doing here, we have a file that's defining the regions of binding for NF-kappa B, and we have a file that's defining our transcript regions. So first what we're going to do is we're going to get the promoter regions, and we're going to define the promoter regions as 2,000 base pairs upstream of each transcript. So you can do that with bedtools blank, and hopefully you can figure out how to do that. So we're going to first get the promoter regions, and then we're going to use a bedtools intersect to find which of those promoter regions overlap with the regions that we have defined as NF-kappa B binding. And that will give us the specific transcripts that are bound by NF-kappa B. Any questions about what we're doing? Yeah.
Just to confirm, NF-kappa B is proteins binding to promoters, which is activating certain transcripts, right? So we're looking for transcripts that are expressed or annotated in this genome, and we're looking for linked promoters and seeing if NF-kappa B is binding.
Great, yep, exactly. So NF-kappa B is a transcription factor.
Yeah.
Transcription factors work on their targets by binding upstream. Depending on the cellular condition, it can be upregulating, it can be downregulating, it can be whatever it is doing. So we have information about where NF-kappa B binds, but we need to associate that information with the transcripts so we can then go look at those genes and say, how are they actually regulated by binding? How are those genes that are bound by NF-kappa B behaving differently in our data set than the genes that are not bound? And what can that tell us about the mechanism of what NF-kappa B is doing to our cells? Okay. So work together, talk to people around you. And if you have any questions, raise your hand. Was anybody not able to make those files that we need, and does anybody want me to put them in a shared directory for the time being? Yeah, that'd be easier. Okay, I'll put those in there. So the GTF and the transcript GTF are both in there, and I'll add the bed file. What's up? Yeah. Okay, so transcript genes have multiple isoforms. So alternative splicing, the transcript ID is linked to a specific isoform. The gene ID is linked to all of the isoforms. So a transcript is specific to the exons that are included, and the gene has
So multiple exons per gene, and also multiple exons per transcript.
So, say you have a gene that's alternatively spliced. Your gene could look like maybe one isoform looks like this, the other isoform looks like this, and it has another isoform that looks like this. All of these have the same gene ID. It's common for all of them.
Does it usually
So when you're looking at the region of a gene, it's defined as the very beginning and the very end. So yes, it's this entire region. But when you look at exons within the gene, it means just this exon, then this exon, and this exon.
So each exon would be separately annotated.
In the GTF file. Yes.
Each gene would be including introns and exons.
Yep, it's just this position all the way to the very end.
About the transcripts.
So then these would be a unique transcript. So this would be like transcript 1, transcript 1, transcript 2, transcript 3. So you'll notice the way the hierarchy in that file works. There will be one gene and there can be multiple transcripts for a gene. So each alternatively spliced isoform is a unique transcript.
So would the first and second have the same observable ones?
They would. But maybe not all of them do. So maybe this one looks like this dude here.
Okay.
This is T4. So yes, a lot of them will be the same start and end points, but have different stuff in between. But then within each transcript, all of the exons are defined individually. Right, so this transcript is going to have 3 exon lines. This transcript is going to have 2 exon lines. And in this case, this exon line will be the exact same, and it will be repeated for this transcript. Because it's the same one.
And for a given set of exons that are related to a gene, we assume there's only one promoter.
Well, this is why we're not looking at it on the exon level. We're looking at it on the transcript level. Because the promoter is always upstream of the transcript. So we're using the start information from the transcript to go upstream from there. If we were using start information from the exons, then we would be looking at multiple locations within a transcript. You know, we'd be starting here and getting those regions. But we're just going upstream of the entire gene, so we want the start point of that transcript. You could also do gene if you didn't want to do the alternative isoforms. That would